Okay, so let's talk about solar radiation. If you're going to have action taking place in the atmosphere, you need some mechanism to provide energy for that. Just like you need energy for your car to run, or you need energy to power your lights at home. Well, the atmosphere needs energy too. So, in order to do that, the atmosphere gets its energy from the sun. And so, part of understanding meteorology and why the weather does things is understanding a little bit, and we're going to keep it very simple here, about solar energy and terrestrial radiation. So let's take a look at these things here. So let's talk about electromagnetic radiation. You hear radio waves. You look outside and you see things with your eyes. These are all radiation. The fact that you're seeing is electromagnetic radiation. So it comes in various wavelengths, as you can see on the chart here. You get X-rays sometimes for something being wrong with you. All of this are different forms of electromagnetic radiation. The sun does the same thing. It puts out electromagnetic radiation, and so does the earth. Interestingly, they're waves. Think about an ocean wave. You have a wave hit you, goes down into a trough, and comes back up again and hits you again. That's just like what electromagnetic radiation looks like. A wave like that. And one interesting thing is about electromagnetic radiation is they move at the speed of light. So they're basically moving 186,000 miles per second. The closer the wavelengths are, the more energy is coming at you. The further apart the wavelengths are, the less energy. All objects absorb radiation to some extent, and then they re-emit that radiation. The earth, the sun, all of them. Both the earth and the sun can be considered black bodies. And since the sun is much hotter than the earth, the radiation coming out of it is far more intense than that of the earth. And it comes at a much shorter wavelength. They're closer together than the earth's radiation. But the earth is a black body. So according to that, we can calculate using Wien's displacement law literally what the different wavelengths would be. Notice temperature is in the bottom. Think about it. The temperature of the sun compared to the temperature of the earth. Wow, what a difference. So the temperature of the sun being so large, the wavelength will be very, very small. Temperature of the earth, about 280 degrees Celsius or so, average. That's a huge difference. That's why the Earth's radiation is called long wave radiation. The sun's is called short wave radiation. And here you can see if you change the temperature, it goes up by the fourth power. So in other words, if your temperature was 2 degrees, you would just take 2 times 2 times 2 times 2. But think about it. The Earth is about, like I say, 280. The sun, maybe 1,000,000. Look at the difference in scale there for energy. All right, the amount of energy reaching the Earth. We are in the Earth so far from the sun. So if you double the distance from the sun, you would reduce the amount of energy coming to you by square of that, or 1/4 the amount of energy. So if you were 3 times from the sun, you would be 1/9. So that's a quick and dirty way, actually, you could estimate how much radiation is coming to a planet that's further and further from the sun. You can see how it goes down pretty quickly. That's why planets in the outer parts of the solar system aren't getting nearly the amount of energy that we are. And if you go towards the sun, like Venus, it's getting significantly more energy. All right, here's the more complex part. Take a flashlight battery. I like flashlight and just shine it down on the surface. If you shine it straight down, you see a small circle. Not very big at all. But if you shine it at an angle, wow, look, it covers a lot more area. The energy coming out of that flashlight is the same. So one, it's spread over a small area, more concentrated, more energy at any individual point in that area. B, the energy is hitting it at an angle, covering a larger area, so the amount of energy is not getting in nearly as much at any one given point. But guess what? The Earth gets that same issue. We call it, take a point at the equator. The sun's directly overhead at least twice a year. So at that point in time, solar altitude is 90 degrees, complete direct sunlight. Most intense radiation you can get on Earth at that point. However, at the North Pole at that time, you're just barely seeing the sun. So you wind up with hardly any radiation because it's mostly skimming across you. And as you come down, like across Alaska and all, you're getting some radiation, but you're not getting a lot because it's spread out over a large area. So as the sun moves north in the summertime, in our summertime, that angle changes and it becomes less and becomes bigger and bigger here, like in Ohio or something and all. So you wind up with much more solar radiation in the summer. But when it goes to the south in the winter, it's a lot less. And here you can see the differences. And here you can actually look at it. The tilt of the Earth never changes. It's always 23.5 degrees. But because of the way it rotates around the sun hitting the Earth changes. Oh yeah, interestingly, in our summertime, we're the furthest from the sun, not by a lot. In the wintertime, we're actually a little closer. So you're actually receiving more energy in the southern hemisphere each summer than we do in the northern hemisphere in our summer. So let's go back here a minute. Solar radiation comes in the atmosphere and all kinds of things happen to it. Part of it's scattered. Think about it. There are dust in the atmosphere. It might hit that dust. What about a cloud? Some of it's reflected. And some of it is absorbed. And all of that has to add up to 100%. Here's what scattering looks like. Particles dispersing at the top of a cloud. They go in all different directions. Some of those are coming down to Earth. And there's what's called a preferential scattering, which is what for blue-violet light by oxygen and nitrogen molecules. That's why our sky appears blue in the summertime or any time of the year. What about reflection? Well, think about it. If you have an ice, how about snow cover in the wintertime when you're outside just after a fresh snow and the sun's out bright, you can hardly see. That's because it's reflecting. The albedo is very high. The amount of radiation that's scattered back into the atmosphere and out to space is very high after a snowstorm. And then there is absorption. In the upper atmosphere, in the stratosphere, a lot of UV is absorbed by ozone. Ozone is a chemical reaction that grabs that ultraviolet light and keeps it from coming to Earth. When we still are having these ozone holes, what happens is chemicals interfered with the ozone, broke it up, got rid of it. So more and more ultraviolet light was allowed to come through to the Earth. And ultraviolet light is not a real good thing for us. It causes skin cancer and other diseases. So here you can see the difference. Lighter the surface albedo. If you look at a satellite picture, if you have snow on the ground, you can really see it brightly. Notice the Great Lakes. Well, guess what? Water mainly absorbs solar radiation. It doesn't reflect it very well. So it's much darker. If you looked here Actually, there's a part in the Adirondacks much darker. It's snowed all around it. It looks very bright. But the Adirondacks have a lot of trees there, make it look a little bit darker. So of this, 30% is reflected by the Earth atmosphere system, 23% is absorbed by the atmosphere, and another 47% is absorbed in the Earth's surface. So that is our energy coming from the Earth. So the Earth is basically a recipient, and you can see it creates temperatures which are basically a reflection of energy. Now, in the lower atmosphere, we have the greenhouse effect. What is the greenhouse effect? We sure hear enough about it by climate change and all, but there are greenhouse gases in the atmosphere that absorb infrared radiation. But they absorb it in the long wave. They don't absorb it in the short wave. So, methane, carbon dioxide, water vapor are all greenhouse gases. They absorb all this radiation that's coming out from the Earth. When the Earth sends back its infrared radiation, its long wave radiation, it gets absorbed by these greenhouse gases. And guess what? They re-radiate some of that back down to the Earth. Some of it goes back into space. A greenhouse gas will radiate like any black body in all directions. So, but that is why we have a warmer surface than we would normally have. Wonderful, normally. However, too much of a good thing is not always what you want. While I like warm weather, I really don't think I would like 190-degree temperatures or 150-degree temperatures that well. So, you want to keep these greenhouse gases in check. They've fluctuated over time, as we all know. They just happen to be a little higher right now than they've ever been. But another one is water vapor contributes much to this. You're going to get asked the question why water vapor is the principal greenhouse gas. Well, where you have a lot of water vapor, take down in Florida, for example, or the southern states, there's a lot of water vapor in the air. It absorbs at night, especially, all that infrared radiation coming back out of the Earth, goes up into that water vapor, and it absorbs it and re-radiates it back down. And what happens is the temperature doesn't cool as much at night there. So in the southern or Gulf Coast states, you wind up with a warmer temperature at night. Now, if you go out in the desert where you don't have any water vapor, same heating and maybe at the same latitude, you wind up with a much cooler night. And that's why water vapor is so important in the greenhouse gas. And we've been looking at calendar effect, and obviously greenhouse gases are going to change because CO2 is part of a greenhouse gas. It's just one of many. But CO2 varies throughout the year because of photosynthesis. So it's going to drop off in the summertime and pick up in the wintertime. The one final thing I just wanted to talk to you and show you a quick peek of today was we can use all this wonderful information that you just learned a little bit of on different satellite images. Say I want to know there are different bands, 0.47 microns. These are all long wave radiation coming from Earth. And each band gives you a different picture. This is basically a visible in the red image. This is blue image. This is vegetation. This is snow cover. These are from cloud particles. There are actually 16 different bands that give different information that a meteorologist can use, and maybe other scientists can use, like a CO2 long wave band. So, hope you got a little bit out of this. This is where all the energy comes in, and you can see it's extremely complex how it's distributed.